In this session, we're going to see about exponential functions and graphs. An exponential function is a function of the form f of x is equal to a to the x. And we may be tempted to think that this looks like a polynomial function, except for one huge difference. The variable is in the exponent, which gives us all kinds of new stuff to consider. When we consider the domain and range of such a function now, the domain is going to be the set of exponents that we're going to put on a base, and the range is going to be, we're going to call them the results. Now, a minute ago I used the word base, and in this case f of x equals a to the x. The base is a, and of course the x is the exponent. Here's the deal. The domain of an exponential function is going to be all real numbers. Anything can be an exponent. We've seen exponents that are whole numbers, say like a cubed. We've seen exponents that are fractions, like a to the 1/2, and recall that that would be the square root of a. And we've seen exponents that are negative, say a to the -2, and that would be 1 over a squared. And if we're going to have anything as an exponent, then we need to have restrictions on the base. And so, noting that we want to be able to square root numbers, the base can't be negative. Noting that we want to be able to take reciprocals, the base can't be 0. And so we need a base that is positive. Furthermore, if the base is 1, the outputs are boring. And so that would be they're always 1. And so a is never equal to 1, that base. So we're looking at bases that are between 0 and 1, or bases that are greater than 1. And we'll explore all of those as we go. In fact, let's look at our first example. For our first example, we're going to analyze and graph the function f of x is equal to 2 to the x. And in this context, for analyzing, we are going to look at the domain, the range, and asymptotes, or there's only going to be one, but asymptote and the intercept. I think a good way to get started would be to consider an XY table. So inputs and outputs, we're going to use, let's say -3, -2, -1, 0, 1, 2, and 3 for now, and see if that does enough for us. F of -3, now that would be 2 to the -3, and the output there is 1/8. Quick mental work will convince us that if the input is -2, 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. That's true of any base that's legit. In fact, that's true of any base that's not 0. 2 to the 1 is, of course, 2. 2 squared is 4, and 2 cubed is 8. Now let's get a set of axes, and we'll see what we can do about plotting some of these points. 0, 1 seems like a good one to look at. And then, 2, 4. We had 1, 2. And 3, 8. And then we had -1, 1/2. -2, 1/4. -3, 1/8. That's getting really, really small, but I think this is a good indicator. And we're going to trace this out into a nice smooth curve. And there we are. We have a graph that sweeps up to the right. That's called exponential growth. And to the left, it's going to hug that x-axis. The deal is that no matter how negative the exponent is, on a positive base, the answer is always going to be positive. And so this is going to hug the x-axis but never touch the x-axis. That is asymptotic behavior. And so this graph is asymptotic with the x-axis, and there is a horizontal asymptote of y equals 0, the number that it will try to become but never actually reach. As such, there will be no x-intercept. There is, however, a y-intercept, and that's the point 0, 1. As far as the rest of the stuff we're looking at, let's go ahead and consolidate our information. The domain is going to be all real numbers. The range is 0 to infinity with an open parenthesis at 0. It doesn't actually equal 0. There is a horizontal asymptote of y equals 0, and then there is a y-intercept of 0, 1. So that's the analysis portion. And the graph is that of exponential growth. And this kind of exponential growth is what happens with investments and populations, among other things. For our next example, we're going to analyze and graph g of x is equal to 2 to the x plus 3 plus 4. Where I see the x plus 3, that's a number that's wrapped up with the input variable, and that is going to turn out to be a horizontal translation. And remember, we changed the sign on those, and so that's going to be to the left 3 units. The plus 4 that's not wrapped up in the exponent, or with the input variable, is a vertical translation up 4 units. Two things that I like to consider where they land when I consider graphing an exponential function. If we look back at the previous example, two things would be the horizontal asymptote, where it goes, and then the point where it crosses the y-axis. We have this as coordinates 0, 1. If I can figure out where those two things go, then I have a pretty good idea about how to draw the graph. Shifting up 4 units means that the horizontal asymptote is also going to shift up 4 units. So is that point where it crosses the y-axis that had been 0, 1. It's also going to shift up 4 units. But then we also have this shifting to the left of 3 units. And I drew that just a little bit low because I didn't want it to interfere with the graph. So the point that would have gone through 0, 1 is now actually going to go through the point -3, 5, right? To the left 3 units and up 4 units. As far as the rest of the graph points are concerned, we can think of where the points had been. You can reference your graph and then plot them accordingly. And then do our best to draw something that's asymptotic and then has that exponential growth. Now we can jot some things down like the domain, which is going to be all real numbers. That's for all exponential graphs, or exponential functions, I should say. The range is not the same for all of them. The range is closely related to the horizontal asymptote. And in this case, the horizontal asymptote, let me go ahead and write that down, is y equals 4. And because this is goes up, the graph does, to infinity, I know that that's the lower limit for the range. In other words, the range is 4 to infinity, with a parenthesis at 4. Finally, for the y-intercept, we can evaluate the function when x is equal to 0, and it looks to me like that's going to be 0, 12, which isn't featured on my graph because my axes don't go that high, but that's what we're looking at. Now we have this new shape in our library of functions, that of exponential growth, but once you know the shape, if you know where to put it, then you can draw the graph. Now we're going to see the effect of a coefficient out front. Here, same instructions, analyze and graph, and our function is h of x is equal to 3 times 2 to the x. As you may recall, a coefficient in front of a function is a scaling factor that can either compress or stretch vertically. Because our coefficient is 3, this is going to give us a vertical stretch. And the impact of that is actually not too hard to obtain. First, we're going to draw in dashed form y equals 2 to the x. So let's consider in yellow the y equals 2 to the x graph, which goes through the point 0, 1, and 1, 2, and 2, 4, and has that exponential growth and asymptotic behavior. I want to look at one point in particular for right now, and that's the point 0, 1. We're going to take the distance between the horizontal asymptote and the y-intercept, and we're going to multiply it by that 3. And so I'm going to put a dot at 0, 3. And that right there is how we're going to consider the scaling factor. So the vertical stretch by a factor of 3 increases the distance between the horizontal asymptote and the y-intercept by a factor of 3. All of the other y values will also get multiplied by 3. And so the y value of 2 now becomes a y value of 6. The y value that had been 4 becomes now a y value of 12. So we have that scaling factor. And so now let me see if I can connect these dots with a curve. And we have here a graph that is asymptotic and has been stretched by a factor of 3. That does not affect the domain, the range, or the asymptote. And so let's write down the domain is going to be all real numbers. The range is 0 to infinity. And the asymptote, the horizontal asymptote, is y equals 0. What it does affect is the y-intercept. The y-intercept is going to be 0, 3. And what we're going to find is whatever that coefficient is out front, as long as the graph hasn't been transformed in any other ways, that is going to give us our y-intercept. So this is the exponential growth curve that has been scaled up by a factor of 3. For our next example, we're looking at the function f of x is equal to 1/2 to the x. And what I'd like for you to do is, using an xy table, see if you can analyze this the way we've been doing. Go ahead and pause the video and see what you can do. So using the same inputs, -3, -2, -1, 0, 1, 2, and 3, we have the same outputs, but they're showing up in different places. We end up with 8, 4, 2, 1, 1/2, 1/4, 1/8. Let's see why, for instance, f of -3 turns out to be 8. We're looking at 1/2 to the -3. Remember, the negative part of that exponent means we're taking a reciprocal. And so this translates to 2 cubed, and hence 8. As for the rest of them, they follow suit. And so plotting these points, what we have is a graph that starts up and to the left and then comes down to being asymptotic but not touching the x-axis. We still have the horizontal asymptote of y equals 0. So let me write down some things. Our domain is still going to be all real numbers. Our range is still going to be the set of positive numbers, 0 to infinity. The horizontal asymptote is still y equals 0. And the y-intercept, amazingly enough, is still 0, 1. So that part is all the same. What's different is that our graph is now that of exponential decay. And this kind of decay occurs with radioactive materials, medicine or drugs in your bloodstream, and things that are cooling off, like soup and dead bodies. And now that we have this shape, if it were transformed, say by moving it to the left or to the right with a horizontal translation or vertical translation up or down, or even scaled, it would all be the same as what we've been looking at with our previous functions. Let's kind of do a mid-session summary here. And what we have here are two graphs, one of which is decay, swooping from the upper left and then asymptotic with the x-axis on the right, and the other of which is growth, asymptotic with the x-axis on the left and swooping up to the right. Both of these are graphs of functions of the type f of x is equal to a to the x. These are our exponential functions. The decay curve is what happens when a is between 0 and 1. In other words, if the base is a fraction less than 1, or any positive number less than 1, then you're going to have exponential decay. If the base is greater than 1, then you're going to have exponential growth. and it's because of how the exponents behave on the various bases. So add these two to your list of basic functions, the shapes of which you should remember, and yeah. Let's look at this next example. We're to analyze and graph y equals e to the x. There's a definition of e, which we'll get to in a different session. For right now, what you need to know is that e is a number, and it's approximately 2.718. And right now you're thinking, this isn't fair. I don't want to represent a number using a letter. Well, you've done it before. We have pi. We have I. Well, we can add e to that, and now we have pi, P-I-E. Anyway, it's one of those numbers that comes up so often that they have given it a name. It's actually called e because of a guy named Leonard Euler, and Euler's name starts with an e. And so e is actually Euler's number. What you really need to concern yourself with at the moment is that e, being 2.718, is bigger than 1. Flashing back to our previous screen, that means this graph would have exponential growth properties. I know that when x is 0, then e to the x, e to the 0 is 1. When x is 1, e is going to be about 2.718. We're looking at e to the 1, e to the first power. And this is basically what I need, because I know that the shape is going to be asymptotic with the x-axis and then exhibit exponential growth. If I needed a perfect graph, I would use a machine. But for now, what we're going to say is that the domain is all real numbers. The range is the set of positive numbers, 0 to infinity. We still have a horizontal asymptote of y equals 0. We still have a y-intercept of 0, 1. And all of these things are true because what we have is an exponential function that has not been transformed. There's no scaling factor. It hasn't been moved. We're just being introduced to this new base right now, the number e, which, as I said, is about 2.718. Okay, so that was maybe a little bit of bad form. Let's look at x and y values. Reminding ourselves that we are looking at y equals e to the x. If x is 0, we're looking at e to the 0, and as long as the base isn't 0, anything with a 0 exponent is 1. If the input is 1, then the answer is e to the first power. If the input is 2, right, if x is 2, then we have e squared. And this is a little uncomfortable, but there's a button on your calculator that is an e to the x button, or an exp button, or something like that. And what you should do is get your calculator out and make sure that you have a way of getting it to tell you that e to the first power is about 2.718. E to the second power is about 7.389. And the reason I say get your calculator to tell you how to do it, for some calculators you're going to type in the E button first, and then you're going to put in, say, a 2, and then equals. For some calculators, you would put 2, and then hit the E to the X button, and it'll just spit out the number. So make sure you know which of these two languages your calculator speaks. And then just to flesh out the rest of this discussion a little bit, suppose we put -1 as the exponent. Then because that means a reciprocal, we're looking at 1 over e, which is approximately 0.3679. I wouldn't expect you to graph that level of detail, but I did want you to see what these numbers tend to look like. Now we're going to do what we've been doing in reverse. Here we have an exponential growth function. We're asked to find an equation of the form y equals a to the x for the graph. In other words, we're supposed to find the base. 2 points labeled on our exponential growth curve are 0, 1, and 1, 5. If we consider these as having come from an xy table, then 0 would be an input associated with the output 1. Likewise, 1 would map to 5 as an output. 0, 1 means that y is 1 when x is 0. So 1 is equal to a to the 0. That actually gives me not a lot of information, because I was already told the equation is of the form y equals a to the x, which means that there's no scaling factor, there's no horizontal or vertical translation. But the 0.01 confirms that for me. The 0.15 means that 5 is what happens when I put an exponent of 1 on the base a. And if you think about that for a couple of seconds, then you'll see that that means that a is equal to 5. Knowing that, our function is y equals 5 to the x. We just had to find the base, and having the 0.15, together with knowing that there was no horizontal or vertical translation or a stretch, was sufficient information. In our next example, we're told to find an equation of the form y equals c times a to the x for the graph that's given. And on the graph are indicated the points 0, 2, and 218. The c as a coefficient means that we have a vertical stretch or compression to consider. That is most readily obtained, I think, by looking at the points that are marked on the graph, in particular the y-intercept 0, 2. Since this is of the form y equals c times a to the x, there's no horizontal or vertical translation, which means that the distance between the y-intercept and the horizontal asymptote is 2. That tells me that the stretching factor, c, is equal to 2. So now we can flesh this out just a little bit. We can say that this means that y is equal to 2 times a to the x. Here's the thing. This point where it crosses the y-axis, whatever that y-coordinate is, that's going to tell me what c is, unless there's a transformation, a translation, horizontal or vertical, going on. Now that I know that y is equal to 2 times a to the x, I can use the point 218 to figure out the rest of it. In other words, y is 18 when x is 2, so we have 18 is equal to 2 times a squared. What we've been glossing right past is the order of operations. That is to say, the base is a, not 2 times a. And the reason I know that is there are no parentheses around the 2a. Which means that to solve for a squared, which I need to do if I'm solving for a, I should first divide both sides of this equation by 2. I end up with 9 is equal to a squared. Usually when we square root both sides of an equation, we need to remember plus or minus, but our bases are not negative. And so if 9 is a squared, then a is equal to 3. This is our base. So our function is y is equal to 2 times 3 to the x. And this was again obtained by considering the vertical stretch by a factor of 2 and an ordered pair x, y that was given to us in the form of 218. For our last example, we're given a function y equals 4 to the x, and we're asked to complete ordered pairs. We have 0, blank, blank, 4, 1/2, blank, and blank, 16. In other words, what we are given is, in each case, either an x-coordinate or a y-coordinate. 0, blank corresponds to an x-coordinate. Blank, 4 means they gave me a y-coordinate. Likewise, 1/2 blank means they gave me x, and blank, 16 means they gave me a y. Now we just have to figure out, for y equals 4 to the x, what the other number is. For the first one, 0, blank, what this means is we're putting 0 as an exponent on forward, so the answer there is going to be 1. So 0, 1 is going to be that first ordered pair. For the second one, what we've got is a y value of 4. So y is 4. And so we're looking at 4 is equal to 4 to the x, because, y is 4 to the x. What exponent on 4 gives me 4 as an output? The answer is 1. And so 1, 4 is the second ordered pair. For the third one, we are given x is 1/2. So we need to figure out y is equal to 4 to the 1/2. And 1/2 is, of course, a square root. And so the output there is 2. And so we have the ordered pair 1/2, 2. Finally, blank comma 16 means that y is 16. And so we're looking at 16 is equal to 4 to the x. We need to figure out the exponent on 4 that gives us a result of 16. Since 16 is 4 squared, the answer is going to be 2. And so that last ordered pair is 2, 16.